can ask chat a quite concrete question, and that would be in this one. I would ask it, um, what is the relationship between when we have like a matrix that defines a rotation or symmetry? How are the determinants? So, what is the relationship between determinant value and when a matrix is defining a when a matrix defines a symmetry, um, rotation, reflection. So quite an open question, but at the same time quite concrete. It's not like a general question regarding all matrices, all everything. So determinants of a square matrix gives important geometric information, particularly regarding area, volume, scaling, orientation, and reflection. That's a general intro to determinants. So here we have some information. The absolute value of the determinant tells you how the matrix A scales volumes. Alright. So if it's bigger than 1, strictly it expands, otherwise contracts, or if determinant is 1, volume is preserved. So for a pure rotation or reflection, the volume isn't changed, it should be equal to 1, the absolute value. If it's minus 1, it means it just switched around. So that's why we take the absolute value. Determinant and orientation. So a sign of determinant indicates whether the transformation preserves or reverses orientation. So determinant bigger than 0 is orientation preserving, like rotations. And smaller than 0 is orientation reversing, reflection, certain improper rotations. Aha. So in 2D, let's talk in 2D. So 2 by 2 matrices. Let's take easy here. Nice example chat gives us. R of theta. So we create like a rotation matrix and it's called R of theta. So chat shows us cosine theta, minus sine theta, sine theta, cosine theta in the 4 entries 2 by 2 matrix. And the determinant is plus 1. It actually worked out. If you determinant for 2 by 2 is this times this minus this times this. So it's cosine squared plus sine squared. And whatever the angle would be, the independent variable trig identity says that's value 1. And reflection matrix across a line through the origin reflects across x-axis. We have 1, 0, 0, minus 1. Determinant is minus 1. So again, the absolute value will be 1. That based on the previous advice. Determinant absolute value is 1. Volume is preserved. Oh, and here we have number 3. Symmetry, orthogonal matrices, and determinant. A represents a rotation or reflection if it is orthogonal. And we can have A transpose A is identity, where I is identity matrix. So, matrix A represents a rotation or reflection if it is orthogonal. Orthogonal matrices satisfy the following. Determinant is plus or minus 1. Nice. So, determinant of plus 1 implies rotation, proper orthogonal. And determinant, if it's minus 1, reflection or improper rotation, orientation reversing. So let's look at this once again. Interesting. And then we have a summary table. So summary table basically says whether if it's orthogonal based on what kind of transformation it is. So if it's rotation reflection, it's orthogonal. If it's scaling shear, no. Alright, so if the absolute value of the determinant is 1, then it's orthogonal. Here with the transformations that they showed. Determinant acts as a quick check. So the absolute value determinant is 1, A is orthogonal, symmetry transformation. The sign tells you if it's rotation or reflection. So rotation is plus 1 and reflection is minus 1. So that's kind of our main point here. We wanted to research, okay, depending on the determinant value, when it's a rotation and when it's a reflection. So here we have a direct information about that. Oh, we can do 3D. Okay, can you please show it for 3D? So one more question, then we'll wrap it up. So if it's in R to to the 3 by 3 represents rotation reflection combination if it is orthogonal. So A transpose times A is identity, or equivalently A inverse is A transpose. Alright, so orthogonal matrices preserve lengths and angles. They also preserve volume or reverse it, so it's gonna go either determinant 1 or minus 1. Determining 3D. 3 by 3 orthogonal matrices. So again, the thing applies, the value is still 1, minus 1. Proper rotation is plus 1, improper rotation is orientation reversing, includes reflections is minus 1. Very similar idea. Here we have an extension of the idea for 3D, 3 by 3 matrix, R subset of theta. Theta is the angle of the transformation, and preserves orientation, volume, unchanged, determinant is 1. Alright. It's pure rotation above the axis. If it's reflection across a plane, then its reflect sub xy can be called, determinant will be minus 1, and the matrix would look this following way. Then the orientation is reversed, volume magnitude is unchanged, but orientation flips. Interesting. If we have improper rotation, which is rotation plus reflection, example could be 90 degrees by z-axis, then it reflects across xy plane. It looks like this, the matrix, and determinant would be minus 1. So that would be the inverse, so volume is kept but inversed to the other side. Okay. It's a combination of rotation and reflection. So we have a summary table for all this again. I mean, this is a lot of information, so if yeah. So I would wrap it up here. It's been informative.